Today we're going to have a look at how we solve a system of linear equations by means of substitution. So we know we have to solve a system of equations, and specifically we're looking at just two equations. That is, we're going to find an x and a y that satisfies both equations. The method that we're looking at today is substitution. Now if we have a look at our notes here, it says that when considering two linear lines defined by linear equations, we can consider two main situations in which they exist. Now the first one is what I've called unique solution, or case 1 over here. Now anytime we have two equations, let's call this one equation 1, this one equation 2, we could put them into y equals mx plus c. Now when we do that, we can see that our first gradient, negative 3 over 2, is different from our second gradient. Now any time that we see this where the gradients are different, we know that there will always be a unique solution. So you can see these two graphs modelled. We can see that our unique solution occurs here. So we might just think by looking at this that the unique solution is x equals 4, because there's 1, 2, 3, 4, and y equals negative 1, negative 2, negative 3. So the solution to these equations can be found algebraically, but what they represent here is a point of intersection. It's a point that is shared by both lines, that lies on both equations. So let's have a look at how we find them by substitution. We said that equation 1 here was 3x plus 2y equals 6, and equation 2 is x minus y equals 7. Well, the first thing we might choose to do is solve for one variable, or in this case we'll solve for y. Remember, that means that y will be on its own. Now, it might be a good idea to do this with the second equation because that looks a bit simpler. So if x minus y equals 7, well, I can subtract x from both sides. Minus y equals 7 minus x. And I can multiply by negative 1, which is to say y equals negative 7 plus x. Now negative 7 plus x, that's the same as writing x minus 7. So I can see here that I've solved for y. I've done that with equation 2. So my second step is to sub this in to the other equation, which we'll use equation 1. So sub this into equation 1. Okay, so equation 1 looks like 3x plus 2y equals 6, and I know y equals x plus 7. So 3x plus 2 times something equals 6, and that something is x plus 7. Now I've got one equation with only one variable x. Anytime I want to solve a system of equations, if I've got 3 equations, I need 3 variables. If I've got 2 equations, I need 2 variables. Now, if I've only got one equation, 3x plus 2x plus 7 equals 6, I can see that there's only one variable x. So 3x plus 2 times x plus 2 times 7, which is 14, equals 6. So I've got 5x plus 14 equals 6. Now that I've got this equation, you might see that part 3, or step 3, is to solve for x, because I solved for y before. So if I subtract 14 from both sides of the equation, I'll get 5x, let's just get that colour right, 5x equals 6 take away 14, which is negative 8. If I divide by 5, then x equals negative 8 on 5. So I've got a value for x. Now the question is, how do I find my value for y? Well, I knew that y equals x minus 7, so once I've got my value for x, we need to find y. So y equals x minus 7, well that is y equals negative 8 over 5 minus 7. Now I can think of this 7 as being negative 35 on 5, because that's like saying 7 over 1. So y equals negative 8 over 5 minus 35 on 5, which is that minus 7. Negative 8, take away another 35, is negative 43 on 5. So, to give my answer in context, I might say x equals negative 8 over 5, y equals negative 43 on 5. So that's where we've got one unique solution. There's another case here, that's where we have no solutions. So we can see here that if we had two lines with the same gradient, but an alternate or a different vertical translation, that's another word for saying y-intercept, or it means the same thing in this context, they'll never intersect. For instance, if equation 1 was 2x plus y equals 5, and equation 2 was y equals negative 2x plus 7, when I put them both into y equals mx plus c, this is what I get. We can see here they both have the same gradient of negative 2, but their plus c, or their vertical translation, is different. If I sketch those graphs, you'll see here that these lines will never intersect. They're what we call parallel lines. Now this too can be found algebraically. This one's a little bit easier, because equation 2 is already solved for y, so my step 1's already done. I already know y equals minus 2x plus 7. Now if I sub that in to 2x plus y equals 5, then I'm subbing in for that y. Now this is minus 2x plus 7. I find the brackets don't matter, so we can get rid of those. There we go. And I can see 2x minus 2x is 0. And I've got 7 equals 5. Now when I see this, there's a fallacy. We know that the number 7 does not equal 5. So if I get something that's mathematically incorrect, I can say, therefore, there is no solution. And that's it. Let's see how we can put this into practice. Solve the following system of linear equations. We've got 2x minus 3y equals negative 8, and y equals x plus 3. Now remember, step 1 was to solve for y. And you'll see here that it's already been done. It's why we choose substitution as a method. So if I know y equals x plus 3, and I also know 2x minus 3 times that y equals negative 8, I can make a substitution. And as you can see, if y equals x plus 3, then I sub that in here. Now it's just a matter of expanding these brackets. Negative 3 times x is negative 3x. Negative 3 times 3 is negative 9. And I just drop that 2x down and that negative 8 down. I see 2x minus x, or minus 3x, is minus x. And now I can bring this 9 over by adding 9 to both sides. Negative 8 plus 9, so that there is positive 1. Now if negative x equals positive 1, that means x equals negative 1. Time to sub that back into that equation there. So I know y equals x plus 3, and that is to say that y equals negative 1 plus 3, which is 2. To put my answer in context, I'll say x comma y, that point of intersection is -1, 2. Let's try another. Now here we have two equations. They're both in the form of y equals. So it might be easier just to take equation 2 and say, okay, well, y equals 7x minus 8. And equation 1, y equals minus 3x plus 2. Well, I already know that y is 7x minus 8. So I can replace that y with 7x minus 8. Now, whenever we're presented with an equation like this, I like to think letters to the left, numbers to the right. So this minus 3x means that I'll add 3x to both sides, and this minus 8 means that I add 8 to both sides. So now I've got plus 3x and plus 8, and what was already there was 7x and 2. This is a little simpler to solve. We get 7x plus 3x is 10x, 2 plus 8 is 10, and if we divide both sides by 10, we can see x equals 1. So that's the first part of this solved, but we still need to find a y. And we can sub this into any equation, we should get the same answer, but I might just try equation 2 again. If y equals 7x minus 8, and I know x equals 1, well, 7 times that 1 is going to be 7. So 7 minus 8 is -1. Now, I could leave my answer like that, but it's always nice just to say that that coordinate xy, that point of intersection, is equal to 1, -1. Our last example for today, we've got y equals 3x plus 9. Let's call that equation 1. And 3x minus y equals 3. We can call that equation 2. Now, once again, y is already equal to something, so I don't have to worry too much. And I can use that to sub in directly into that equation 2. So 3 lots of x minus y equals 3. Well, I know that this y is going to be 3x plus 9. So that's from equation 1. The trick here is when expanding this bracket, a lot of people get the minus 3x, but they forget about the minus 9. And sometimes they'll forget about the negative altogether. I've got 3x minus 9 equals 3. When I see that 3x minus 3x is 0, I get the answer -9 equals 3. Now, we may have to remember that that's impossible. So whenever I see this, I'll have to say, therefore, there are no solutions. These lines are parallel. Now I could prove this too. If I take equation 2 and said 3x minus y equals 3, well, I bring that 3x over as minus 3x, so minus y equals minus 3x plus 3, and if I multiply both sides by -1, that becomes positive, that becomes positive, and this one becomes negative. So y equals 3x minus 3. Now you can see here in our first equation, I had a gradient of 3. I also have that in the second equation. So the gradients are the same, but the plus c, that vertical translation, is different. So there's further proof that these lines have no solution.